Okay, welcome back. In this video, we're going to talk about balancing nuclear reactions. So if you're watching the video, please have your guided notes open, chapter 2, and we're talking about balancing nuclear reactions. So please go there. Fill in your notes as we go through, guys. This is a little tricky for a lot of students. But we're going to go slow. We're going to try to explain it as slowly as possible, and hopefully it will start to click by the time we're done. Okay. So balancing nuclear reactions. There's this thing in science you always hear about, the law of conservation of something. What does it mean to conserve something? Like if you were to conserve water, what does that mean, guys?
You save it.
Yeah, you save it. Well, the law of conservation of matter is kind of the same thing. You're trying to save matter. It says that matter can't, or it can neither be created nor destroyed. So you can't create it, nor can you destroy it. So whatever you have at the beginning, you're going to have at the end, right?
What about entropy?
We'll talk about that, yeah. But for right now, you can't create matter, nor can you destroy it. Good? That's what law of conservation of matter says. So in order to balance nuclear reactions, you must have the same number of neutrons, so same number of neutrons and protons on each side of the arrow. You're supposed to fill in something there with your notes. Okay, so you're going to have the same number of neutrons and protons on both sides of the arrow. Okay, now here's the arrow. What does that mean? Well, that means a reaction has happened. We start with this substance. Okay, and then this reaction happens with the arrow, and we produce these substances. So it broke down, didn't it? It broke down. We had one starting material, and we ended with two substances in the end. So, but we always got to go back to, we have to have the same number of neutrons and protons on each side of the arrow. So, for example, let's start right here. What is this number telling us, guys? That's the atomic number. It's telling us what, guys?
The amount of protons.
Protons, the amount of protons. So Ra, if you look it up on the periodic table, look at number 88. It's called radium. It's got 88 protons. So what do you think we got to have on the other side of the arrow? How many protons total? 88. How many do we have here? 2. And how many here? 86. What's 2 plus 86?
88.
So is that balanced?
Yeah.
It's balanced. Okay, so that's the same number of protons on both sides. What is this number right here, guys?
226.
226. It's called the mass number, right, Oakley? It's called the mass number. So we better have 226 on the other side. How many is right here? 4 and
100 or 222.
222. What's 222 plus 4?
100.
226.
226. Are we right? Are we balanced? Are we good?
We're good.
Yes. That's what we're going to be doing today. But I want to, more importantly, I want you to understand what's happening here. Ra, radium, it must be radioactive. Okay? It's unstable. The nucleus is unstable. So what does it do to become more stable? It gives off what, guys?
Proton.
Radiation. What particle is this? What kind of radiation did it give off? That's an alpha particle. So it must have had too many protons in its nucleus. Those protons are pushing apart, like charges repel. To overcome that instability, it shoots off, or gives off, a radioactive particle known as an alpha particle. And who did it become? What is Rn? If you look at the periodic table. Rn sits over here, guys. What's it called? Radon. Okay? So radon must be a little bit more stable than radium was. Okay. Does that make sense? We're balancing them. We got to have the same number of protons and neutrons on the left side of the arrow as we do on the right side of the arrow. Okay? So, in your guided notes, it wants you to write down an alpha reaction here. And so, here's what you are supposed to write down. So, I'll give you a second. This is the alpha one. You're going to write down this whole reaction. where it says alpha, number 1. So take a second to do that. Then, if you get that finished, write down the beta one on number 2. And then gamma. This is bottom one. So take a second to write those reactions down, and then we'll talk about them. We'll make sense of it all. Okay. If we look at alpha, let's look at alpha first to explain what's happening here. We have uranium-238. It's unstable, it's radioactive. It's going to give off radiation. What radioactive particle is this? This is an alpha particle. So I want you to circle that, or box it, and put alpha. That's an alpha particle. So when you see a nuclear reaction like this, you're going to be looking for what particle or what kind of radiation is given off. So you look to the right side of the arrow and try to find one of those radioactive particles. Let's go to beta. Okay, we got thorium-234. Where's the radioactive particle? I want you to circle it or box it, something, and then let's label it. That is a beta particle. What really is a beta particle? What is it? Why does it have a -1 here and a 0 up here and an E? What is it? It's an electron. Remember, it's a neutron being converted into a proton and an electron. It keeps the proton, and the beta particle is emitted from the nucleus. So why would an element go through beta decay? Well, if it has too many neutrons in its nucleus. Okay, let's go to the last one, gamma. Now, gamma radiation usually will accompany alpha or beta. So whenever there's an alpha particle or a beta particle given off, there could be a gamma ray given off as well. And so we see that uranium-238 is unstable, it's radioactive. What kind of radiation did it give off here? That's an alpha particle, 2 protons, 2 neutrons. It became thorium-234, but what else did it give off? What is this called, guys? It's a gamma ray. Now, it has a big 2 out in front. What is this 2 telling us? Oops. Gave off 2 gamma rays. Okay. So when we go through these equations today, these reactions today, I want you to be looking for what kind of particle is given off. It could be alpha, it could be beta, or it could be gamma. And we're going to balance them. Okay. Let's do practice problem number 1. Stay with me, you're going to get the hang of it, I promise, if you look up here and we watch through how to do these problems. So it says, identify the missing particle in the following nuclear reaction. Now, here's the arrow. That means the nuclear reaction happened there. We know from the law of conservation of matter that you got to have the same number of protons and neutrons on the left side of the arrow as you do on the right side of the arrow. So knowing that, how many protons do we have on the left side? 43. How many so far do we have on the right side?
-1.
A -1. So what do I got to have here?
42.
But a -1, 42 minus 1 is
Oh, yeah.
41. So what would I have to have? 44. Good job, Dallas. So 44, because 44 minus 1 is 43. See that? Okay, now let's do the mass number. 99 on the left side of the arrow. We've got to have 99 on the right. How much do I have so far? 0. So what's left? 99. Okay, now those are our atomic numbers, but what element is it? Hopefully you have a periodic table out. What element is atomic number 44? Ru.
Yes.
Good. So we're just going to put an Ru next to it. Okay, and there's your missing particle. It's your missing element. So, Tc, unstable, it's radioactive. It gave off a what, guys? What is that? It gave off a beta particle. It must have too many neutrons in its nucleus, so it gives off a beta particle and became Ru. Is Ru more stable? Must be. Okay, what kind of radiation is given off? And you should circle that beta particle and call it a beta particle. Okay, let's try another. Practice problem number 2. Okay, we got 2 things on the left side of the arrow now, but the law of conservation of matter is still the same. Whatever you have total on the left has got to add up total on the right. So, let's start with atomic number. I always think that's maybe a little bit easier. What's 4 plus 1, guys? 5. So I better have 5 as the atomic number on the right. How many do I have so far?
2.
2. How many's left? 3. That will balance it. Okay. Now let's do the mass number. I've got 9 here, and what's 9 plus 1? 10. I've already got how many on this side? 4. So what's left? 6. Okay, now we've got to name the element. What element is that? Yeah, atomic number is 3. If you look at your periodic table, that is lithium. So, let's see what happened here. Be must have been radioactive. It became who? Lithium. What particle is this? That's an alpha, so please circle it and put alpha. That's an alpha particle. Okay, practice problem number 3. Let me give you a second. You guys try this one. See if you can get the right answer. If you're watching the video, hit pause. Try it and then come back and see if you get it right. Okay, this one's a little tricky. Anytime they throw in a beta particle, it makes it a little more complicated because of the -1. But I think you guys can still get it. Let's do the atomic number first. How many do we have total on the left side? 3. So we've got to have total on the right side is 3. How much do I have so far? So we've got a 2 and a -1. So what's my total? 1. So how much do I need? 2. Okay? Because 2 plus 2 is 4. -1 is 3, and that's what we needed. Let's do the mass number now. I've got 6 and 1. So 7. Okay, I've got to have 7. I've got 0 right here and 4. So I've got a total of 4. What's left? 3. Now the atomic number is 2. What is it? Number 2 is He, helium. Okay, now I haven't talked about this before. What is that, guys? Does it have a proton? No, but it's got a mass number of 1. So what is it? It's a neutron. And a neutron, they always give a little symbol of a little lowercase n. That's a neutron. So what they've done is they've shot a neutron at this lithium atom, and it broke apart, giving off what kind of radiation? Beta radiation. And what? And alpha. Okay. Good job. Okay, number 4. See if you guys can solve it. Identify the missing particle in the following nuclear reaction. Okay, so far on the left side we don't have anything. on the right side, we've got 21 and a minus 1. So total, we have what?
20.
20. That means on the left side I better have 20. And since there's only one particle, it's going to be all 20 of it. Okay, let's do the mass number. 0 plus 47. What is that? 47, so I need all 47 there. What element is that?
CA.
Yeah, if you look up number 20 on the periodic table, that's Ca, calcium. So calcium gave off what kind of radiation?
Beta.
That's a beta particle. Hey, is this stuff easy or what?
Yeah.
Pretty easy. Okay. Okay, practice problem number 5. Now, there's a little bit of a wrinkle with this one, so let me go through this one with you. Okay. So total on the left for atomic number is 64, right? So, but it's got. We've never seen this before. This number out front is called a coefficient. It's got a coefficient of 2. What does that mean?
There's 2.
That there's 2 of these alpha particles. So how do we find the atomic number if there's 2 of them? Well, you take the coefficient and times it by each one of these numbers. So 2 times 2 is what? 4. What would the mass number be here? 8. And I kind of just write it above and below like that so I remember what the product was there. Okay, now if we have 64 total on the left, we need 64 total on the right. We've already got how much? We already have how many, guys?
4.
4. So how much is left?
60.
60. Okay. Let's do the mass number now. We have 148 total on the left, so we better have 148 total on the right. How much do we have right now?
8.
8. So what's left?
140.
140. Now we just got to look on the periodic table. Which one is atomic number 60?
And
60. Yeah, look at the very bottom. Nd, neodymium. Nd. What kind of radiation was given off, guys?
Alpha.
That's alpha, so please make note of that. How many alpha particles?
2.
2 alpha particles. Okay. Good job. So that's how we deal with the coefficient. Again, we just times it by the number that's next to it. So 2 times 2 would be 4. 2 times 4 is 8. And that's how you figure that out. Okay, let's try number 6. You guys try this one now. Okay, let's see if you got it right. The atomic number is 64 on the left, so total on the left is 64. We better have 64 on the right. How much do we have right here?
0.
0. How much are we going to have on top?
0.
0. Okay, so what's left?
148 and 64.
64 on the bottom and 148 on the top. What element is that? Same element, isn't it? GD. What particle is this?
Gamma.
That's a gamma ray. So is it a particle? No, it's just a ray. It's an energy. So does it change the identity of the element?
No.
No. What's the difference though? This one has more what?
Radiation.
That has more energy. This one's high energy. The nucleus must have a lot of energy, which makes it unstable. So it gives off gamma radiation and becomes, it's still the same element, but it becomes more stable. It has less energy in this nucleus. Okay, good job. And it gave off 2 gamma rays, yeah. Okay, number 7. Take a second and see if you can get this right. I'm going to do it on the board. Don't look up until you've got yours solved. Okay, did you guys get the same thing I got? Did I do it wrong? Okay, let's see. Let's go through it. 3 times a minus 1, guys, is what? Minus 3. What's 3 times 0? 0. So that's why I wrote those numbers like that. So far I've got a minus 3 and 20. What is that?
17.
That's 17, right? And so I've only got one element over here, so it's got to be all 17. It's got to come from that. Okay, now I've got 40 as the mass number and 0. So total I've got 40. What's left?
40.
All 40. So we look up on the periodic table what 17 is, and that's chlorine. So that'd be your answer. And what particle is given off? What is that, guys? That's a beta particle. How many beta particles were given off? 3 of them. So chlorine, why would it do that? Why would it give off 3 beta particles? Too many what in its nucleus? Too many neutrons. Yeah, you give off beta if you have too many neutrons. So it's trying to get rid of those neutrons. Okay, good job. Now let's switch it up a little bit. I'm going to go through this one with you because we haven't done a problem like this. But it says on practice problem number 8 to write the alpha decay of radon 198. So how do we do that? Well, you're going to need a periodic table. Okay? Radon, let's find it. Where is it? What's its atomic number? 86. So radon has the symbol of Rn, and its atomic number is 86. So we're going to put that right here. What was its mass number? What do I write for the mass number? Yeah, that number right here is the mass number. So 198 goes here. Now it's called alpha decay because this thing is going to break up. Just like, when something dies, it decays, it breaks apart. This radioactive element is going to decay and give off what kind of radiation? Alpha. Okay, so what's the symbol for an alpha particle?
4, 2,
Good. 4, 2, what? He. Okay. Now we can figure out what's left, right? So we've got 86 total on the left for the atomic number. So far we got 2. What's left? 84. We have 198 total for the mass number on the left. So far we've got 4 on the right. What's left? 190 what? 194. What element is 84?
PO.
PO, yes. So we're just going to put PO right there. So if radon 198 went through alpha decay, we give off an alpha particle and become PO. Good job. Let's see if you guys can do one of these. Practice problem number 9. There's only a couple left. So number 9, I want you guys to see or to write the beta decay of uranium-237. Oh, it does? Sorry, we're going to have to switch that. So in your books, switch it to beta decay. Yep, you need to fix that. So in your books on this problem, change it so that it says the beta decay. So in your books, make sure it says beta decay. All right, so we got uranium. The symbol, what's the symbol for uranium?
U.
U. What's its atomic number?
92.
92, so that goes to the bottom left. What's our mass number in this case? 237. Okay, now what's the symbol for a beta particle?
B.
0 minus 1 with a what? With an E. Because it's really just an electron, right?
Yeah.
So 0 minus 1 electron. Okay, so now we can figure out what our missing element is right here. So far I've got 92 on the left, total. And I've got a minus 1 so far on the right. What's left? So what minus 1 is equal to a 92?
93.
93. Okay. Total on the left side, I got 237. So far, I've got 0. So what's left? 237. What is 93? NP. So that would be the beta decay of uranium-237. Good job. I notice on your books there's another error. On practice problem number 10, the one that you're going to do now, it should say gamma decay. So make sure in your books that you switch that. It should say gamma decay. And then see if you can write that. Write the gamma decay of plutonium-244. What's the atomic number for plutonium, guys?
94.
90 what?
94.
94. Okay, our mass number, it gives it to us, is 244. All right, what's the symbol for a gamma ray?
0,
0, 0. Yeah, and there's a lot of books will write it differently. I'm just going to write lowercase g this time. But could have you also wrote 0, 0 capital Y, 0, 0 lowercase y? A lot of books write gamma a little bit different for some reason. So I'm going to try to expose you to all of them so that you're just used to it. Okay, what's left? It's the same thing, right? 244 is left and 94 is left. And 94 protons is plutonium. Okay. Very good. So that's how we balance nuclear equations and nuclear reactions. We're trying to find out which particle's given off and what it becomes. And so hopefully that makes sense. We always have to follow that law of conservation of matter. You can't create or destroy protons or neutrons. So whatever you have on the left side of the arrow, you've got to have total on the right side and vice versa. So anyway, hopefully that helps. We're going to do, we've learned enough now to do a worksheet in the book, in the student workbook. Take your student workbook, flip it over a few pages. You now know enough to do balancing nuclear equations worksheet. There's nuclear decay worksheet on the back side of that one. So if you'll take a few minutes now, let's see if we can get these 2 pages down here in the workbook.